Good afternoon, everyone. This is Sam from Fronius, Australia. Thank you for joining us for today's webinar. Today's webinar's topic is Volt-VAR and Volt-Watt response solutions with the Fronius. So I am going to start this webinar now. We have got enough installers. All the installers have joined us for the webinar, so I'm going to start this webinar now. So welcome to the webinar. Today's topic is Volt-VAR Volt-Watt response solutions with the Fronius. Sitting alongside with me is Peter. He will be covering a few slides on how to enter the Volt-VAR settings on a Fronius inverter. So he will show you how to calculate the Volt-VAR value using the Fronius Excel tool, and how to enter those values on the screen of a Fronius inverter. Okay, so he's sitting alongside with me.
Hello everyone, this is Peter here from Fronius Tech Support.
Okay, so let's get the webinar started. Some of you already know that the 24-hour sun vision is the Fronius visions. We believe in a world where 100% of the global energy requirements will come from 100% of renewables. It is a very ambitious visions, but we believe that it is achievable. And the technologies now exist that will help us to achieve that visions. Now, solar energy will play a key role in the mix of renewable, as we know that it's available free of charge, and it's available every day. So in order to harness these huge potentials, Fronius has been developing solutions to generate and exploit solar energy for residential, commercials, and industrial solutions. So if you look at these visions here, we have a few houses with the PV system installed, and it's sort of like a communal storage unit where all those houses are storing energy into this central storage unit and sharing their stored energies in the evening. So we believe that that will also happens. We also have the commercial properties fitted with the solar panels. So Fronius short-term vision is actually storing the energy into the batteries and use that energy into the evening. But we do have a long-term vision, which is you storing the energy in the form of hydrogens and use that store energies in winter months. So we are also working on a few projects where we can also store the energy in the form of the hydrogen, which is our long-term visions. But our main focus at the moment is on the short-term storage solutions. Okay. Now we strongly believe that if we wanted to achieve that visions, an ideal PV systems needs to meet these three principles. One of the principles is that the PV system needs to be flexible. So if you're installing a PV system now, it needs to meet the demand of tomorrow. So we will see later on how Fronius inverters is able to meet the demands of tomorrow's. Fronius Galway inverters, which we launched in the year 2013 or 14, that inverter series can also meet the requirement of the Volt-VAR or Volt-Watt response modes. Okay, so that's one of the principles that we need to make sure that the PV systems is satisfied. The second principle that we believe in that this PV system needs to be reliable. Now, system uptime is the key components of any energy supply, and maximizing the system uptime therefore should be the first priority in any PV systems. All the Fronius inverters are designed with the serviceability on site, monitoring inbuilt, and also with the Fronius on-site support tools, you can be sure that the system is up and running within a reasonable time, and so that we can maximize the system uptime. The third principle that we believe that the solar energy produced from a PV system needs to be optimized. The optimizations of a solar energy is also a key component. Gone are the days where the feed-in tariff was the key driver behind the installations of PV systems, but what we need to consider now is how we can actually optimize the generated solar energy in the form using a different energy management solutions. So the Fronius inverters, as some of you may have installed the energy management functions using a relay. So you also need to consider how we can optimize the solar energy. So we believe that these are the three principles that an ideal PV system needs to meet in order to achieve the 24-hour sun vision. So today's topic is about the Volt-VAR and Volt-VAR response mode. It is it's not a new topic. It's been now specified by the utilities across the countries. Many utilities already started requesting installers to set those Volt-VAR and Volt-VAR response mode on the inverters. But before we go into details, I would discuss the few definitions of the active power, reactive power, what power factor is, and how we can actually calculate the values and enter their values in the Fronius inverter. So what you're seeing in this slide, the active power, what it means is that you have the voltage waveforms, which is represented here in the blue color. We also have the current waveform, which is represented in the red color. And as you can see, the voltage and the current waveforms are in sync with each other. What that means is voltage and current waveforms is hitting the maximum point as well as the lowest points or the minimum points at the same time. Okay, and also it's crossing this 0 point at the same time. Okay, so whenever we have a voltage and the current waveform are in sync, there is no power factor. So the power factor in this case is 1. Okay, now if we would want you to calculate the instantaneous power of their waveforms, there's a few ways we can do it. Now, some of you may have heard of this beer analogy that's widely used in the world. What it's showing here, that if you understand how the beer works, then you won't have any problem with the power factor. So if you know how the beer works, right, and you can easily understand what is a kilowatt, what is a kVAR, and what is a kVA. So it's a really great analogy to understand the reactive power. So what you're seeing here, that this is the beer jug or pint, whatever we call it here in different states of Australia. So this is the beer capacities. That's the actual beer, and the foam on the top of the beer jug or pint is the kVAR. So the foam represents kVAR, the beer represents kilowatts, and the actual capacity is represented using a kVA. So if there is no power factor, if the power factor is 1, and if we wanted to calculate the instantaneous power, the way to do is, as you can see, that the power is actually the multiplications of the voltage and the current. So V times I will give us the power. Negative minus negative also give us the positive power. And this is the waveform of an active power. So in this case, if we wanted to count, this is just an instantaneous value of the power, but the power is always represented in the engineering term we call the RMS value. So root means square values. How can we calculate the RMS value? Well, basically we take the average of that waveforms using this equation. So whenever you take the, so this is the blue represents the average of the voltage, and the green is represents the average of the power. So this is your average power when the power factor is 1. Okay, what that means is the voltage and current in sync with each other. So this is how we can calculate the average power. Makes sense. This is easy to calculate, and using these equations. Okay, so at the moment the cos phi is 1, so your actual active power is going to be voltage times current. Okay, now the things become interesting when we start talking about the reactive power. What you're seeing here is the current waveform is leading compared to the voltage waveform. So as you can see how the current waveform is hitting this point before the voltage waveforms. So the reactive powers is, in that case, we can say that we have a leading power factor of 90 degrees. Okay, so the power factor can be sometimes represented in terms of degrees, or it can also be represented as terms of 0.8 leading or 0.9 lagging. We'll cover the definition of the power factor in the next few slides, but this just this slide is showing the voltage and current waveforms whenever we have a power factor of 90 degrees. And this is the worst case scenario. And why it's a worst case scenario? Because now if we would like to calculate the power, and power is always the V time I's, and as you can see, this is the power waveform, which is the V time I. And if we really want to take the RMS values of the power, then we're going to have to take the average of these instantaneous power values. Okay, so as you can see, this green waveform, when we take the average, is going to be 0. So on average, if we have a power factor, of 90 degrees, cos 90 will be 0, and we're going to have the no real power, which is the worst case scenario. Okay, the power factor in the commercials buildings ranges from 0.85 to 0.95 lagging or leading in some situations. Okay, so I just wanted to give you a quick overview on what happens when the power factor is 90 degrees. There is no real power flowing through that transmission line. Okay, so this is what it shows. Power factor 90 degrees, we have a 0 power. When we take the average using this equations, P is equal to UI cos phi. U actually represents the voltage here. A lot of the countries in Europe, they represent the voltage as U. Okay, so don't get confused with this U. What U is used actually the voltage. Okay. Now reactive powers. When we talk about the reactive power, we also need to consider the power factor. So the power factor can be leading or lagging. Just quickly cover the definitions of what the leading power factor is and what the lagging power factor is. Whenever we have a leading power factor, that means the current is always leading the voltage. So as you can see in this figure, that the voltage is actually lagging and the current is leading. So how you can see here, the current is hitting this point before the voltage. So this is called leading. What's the lagging power factor? It's the opposite. So the voltage is leading the current waveforms. As you can see here, the voltage is hitting this point before the current waveform. Okay, so this is called the lagging power factor. Whenever we do a phase diagrams in the terms of engineering, you can also draw the phase diagrams, and based on that you can calculate the active power, reactive powers as well. And this is just showing that this is the voltage curve, and then it's showing that the current is actually leading the voltage. In this here, the current is lagging the voltage. Okay, and the angle between the V and I is the power factor, the cos phi. Okay, that's just that's how we understand the power factor. Okay, so this is about the leading power factor and the lagging power factors. Now, what happens whenever we set the leading power factors on an inverters? We call that the inverters is actually in the overexcited mode or a capacitive mode. That means the reactive power is supplied to the grid and the grid voltage rises. So this one here, that's for the leading power factor. So the capacitive mode is also shown on the inverter display screen by a positive sign, and that inverter acts as a capacitor. Okay, so with the leading power factor, the inverter acts as a capacitor. In the underexcited mode or inductive mode, reactive power is taken from the inverter, the grid voltage falls. Okay, with this mode, the inverter display screen, the lagging power factor is shown as a negative. Okay, so minus or negative, and the inverter acts as an inductor. Okay, so you just have to note the difference between the leading power factor and the lagging power factors. Whenever we have a leading power factor set on the inverter acts as a capacitor. Whenever we have a lagging power factor or the lagging power factor set on the inverter acts as an inductor. Okay, what that means is that this is basically the diagram shows, or the figure shows, the range of the power factors. So each inverters, if you look at the data sheet of the inverters, there will be a mention of what's the power factor that you can set on that inverter. So the Fronius inverters on the Galva, you can set it from negative 0.85 to positive 0.85. And with some of the other inverters, you can also go as low as 0.8 or 0.7 as well to negative positive, so negative 0.7 to positive 0.7. Okay, so you always look at the data sheets and see what's the power factor value, or what's the range is for that inverter. Okay, and reactive power is always represented with this VAR, so VAR or kVAR. You would probably have seen that in a commercial's electricity bills. The effective power, which is the real power, is represented in watts, whereas the apparent power is the combinations of real power plus the reactive power, and it's given in VA. So sometimes you may have heard of a VA rating of the inverter. Okay, so that's the apparent power of the inverter. Now, let's move on to the this really easy to understand sort of figure. What it shows how the power lines look like out in the street. So this is just a sort of simple basic block diagrams which shows what happens to the AC voltage in the grid without PV systems connected. Okay, so whenever there is no PV system connected to the power lines in the area, what happens? So what it shows here, this is the medium voltage grid, and then we have the transformer on the street, which basically converts the medium voltage into the low voltage. And then once we get the low voltage, which is around 230 to 50 volts, then it's distributed to the different houses in the street. So this one showing no PV system connected, and whenever we have these sort of situations, as you can see, the voltage drops. So as you go further away from the transformer, the voltage will drop because of the resistance in the line. So the houses at the end of the line will possibly, or would possibly get a voltage drop of up to negative 10%, okay, depending on this resistance on the grid lines. So these houses may get, you know, about 8% voltage drop, whereas the house close to the transformer may not have as much voltage drop. Okay, so this is a good way of understanding what happens to the grid lines when there is no PV system connected. Let's look at the grid lines and what happens to the grid voltage when the PV system is connected. I'm sure some of you have also heard about what the voltage rise issues that's been happening in different states of Australia. So what's really happening at the moment is whenever we have a PV systems connected to the grid lines, we get a voltage rise on the grid line, okay? And the reason why there is a voltage rise on the grid line is because the inverter will have to increase its own voltage to send the energy back to the grid, okay? So depending again on the resistance of the line, this inverter here connected at this point of the power line will have to work really, really hard to send the energy back to the grid. And this is where we have a voltage rise at that property. Okay, so as you go away from the transformer, we have the voltage rise right at the end of the line. Okay, and this is a very, I think, common topic now in the industries, and I think a lot of installers are also facing these issues out in the field. And this is the reason why we have this voltage Volt-Watt response mode and Volt-VAR response mode on a Fronius inverters, and we'll show you how it actually helps at least reduce the effect of the voltage rise, okay, in the previous systems. Voltage response mode, as I said, the main objective of having the Volt-VAR response mode on a Fronius inverters is that to increase the number of systems which can be connected at a point to the grid without affecting the voltage within the electrical installations. And because with the increasing solar penetrations, we have experienced voltage rise issues, but this Volt-VAR response mode help us to reduce the effect of the voltage rise. Okay, and to help control the grid voltage, several power quality response mode were introduced in the AS 4777 2015. That is how they've stipulated in the AS 4777 2015. Basically, as you can see here, those tables are already specified in the standard. So what you're seeing here in that table is that we have a 4 voltage values given, AC voltage values given. Again, this is for the New Zealand default voltage. So if you are in New Zealand, then you need to consider this voltage values. And this is the Volt-Watt response set point values. So what happens when we have a 250 volts? The inverter needs to reduce its power at 250 volts. Okay, so when you go from 250 to 265 volts, the inverter must reduce its power up to 20% of its maximum watts capacity, okay, on the nameplate of the inverter. please note, this is an important note. There is a bit of a confusions about when this Volt-VAR response mode is considered. It's only considered when the inverters is try to produce the full capacity, full watt capacity. Okay, so in the Volt-VAR response mode, it needs to be the maximum watt capacity of the inverters. If the inverters is a 5 kilowatt inverters, and if it's trying to produce the full power, then this Volt-VAR response mode will come into play whenever we activate this functionality on a Fronius inverter. But otherwise, if the inverters, let's just say if you've got a 5 kilowatt inverters and inverter is only producing 2.5 kilowatt, half of its capacity, it does not come into effect. So this is a very interesting, very important point here. Okay, and as you can see in the graphical form here, we got a 3 voltage value. So the output power remains 100%, but as soon as the voltage increases, it needs to drop its power. Okay, depending on this value specified in the table. Okay, so here, when the voltage increases from 250 to 265, the drop has to be 20%. This is a 20% drop. So this is a 265 volt here. Okay. And there is another response mode that was introduced in the new standard for inverters, and that's called Volt-VAR response mode. What it is basically that there are 4 voltage values specified in the tables, and we also have these 4 reactive power values specified in the table. Okay, so that means we'll have the 8 set points in total. Okay, Peter will show you how to calculate those set points, but I just wanted to explain you how to understand this table. Okay, so you have a 4 voltage values, and then we have a 4 power factor values given in the table. So what you're seeing over here on our inverters, we have the nominal voltage value of 230 volts. Okay, so that's with the Fronius inverters. We always consider the 230 volt is the nominal voltage value. Okay, so what you're seeing here in this graph, that whenever we have a voltage drops or the AC voltage at the inverter terminals around 207 or at 207 volts, we need to have a power factor of 30% leading. Okay, so there's a 207. Once we set these set points on a Fronius inverters, it will then produce the power with a 30% leading. Okay, whenever there is a voltage of 220 volts at the inverter terminals, no change to the power factor of the inverter. Okay, whenever the voltage is sitting at 250 volts at its terminals, again, we don't have to change the power factor. The inverter is not going to change its power factor. Okay, but as you can see, as soon as the voltage goes above 250 volts, then and reaches the 265 volts, this is the voltage rise. Whenever we have a voltage rise at the inverter terminals, the inverter will produce its power with the 30% lagging power factor. Okay, so this is a 30% lagging power factor. But no changes here. So there's a inverter is not going to change its power. Once again, the important note is only varies the output power when the inverters try to exceed the maximum kVA nameplate capacity of the inverter. Okay, so when we have a 5 kilowatt inverters installed, and when the inverters is trying to produce the 5 kilowatt, then this set points will come into play. Okay, then this Volt-VAR response mode is activated on the inverter. But when the inverters is producing, for example, 5 kilowatt inverters is producing 2.5 kilowatt, then the Volt-VAR response mode is not activated. Okay, so that's why there's an important note here. Really important to consider that. Okay, so I guess in Australia and all the other parts of the world as well, we don't get situations where the voltage, the AC voltage, is dropping below 220 or 210 volts. It is not something and that we come across with quite often, but what we do come across with in many times, that there is a voltage rise. So the voltage is rising from 250 up all the way up to 265 to 70 at some sites. Okay, so in that case, if the voltage is going above 250 volts at the inverter terminals, inverter will produce its power with a 30% lagging. Okay, and it will act as an inductor. Okay, so those tables for the Volt-VAR response mode and the Volt-VAR response mode stipulated in the AS 4777 standard, but there are also some grid operators in different states. They have their own requirements too. Okay, and this table varies from site to site. Some utilities may have got the same table for all the sites, but these tables are specified by the grid operators in the country, okay, or in the states. This is just an example of how the tables for the Volt-VAR response mode and Volt-VAR response mode looks like. Okay, so in this case, I think we only need to consider the Volt-VAR response mode. So as you can see, there are 4 voltage values given or specified in the table, and there are 4 power factor values also specified in the tables. So that means we require to enter 8 sets points in totals to the inverter. Okay, and Peter will show you how to do that. So what it means is that whenever the AC voltage at the inverter terminals is 207 volts, the power factor of the inverter needs to be 0.95 leading. If the AC voltage is 220, power factor is 1. If the AC voltage is 248, again the power factor is 1. But as soon as we have the voltage increasing up to 253 volts, the inverters needs to produce its power with the 0.9 lagging power factor. Okay, and this is just the graphical form of these tables. It's just shows the same thing what we have here in table, that whenever we have a 207 volts, 0.95 leading power factor, no changes required here. As soon as the voltage rises, we need to have the 0.9 lagging power factor on the inverter. Okay, and just important to note there as well that on a Fronius inverters, the nominal AC voltage value is 230 volts. Okay, and also there are some over voltage, under voltage values that's also specified by the Ergon and Energix, which can also be set on the inverter screen of a Fronius inverter. Okay, so it's another example of how the Volt-VAR response mode table and the Volt-Watt response mode table look like. This is an example from an SA Power. Just wanted to point out the difference between these tables from SA Power and Ergon and Energix. So what you're seeing here, see how this table for the Volt-VAR response mode, we got the 4 voltage values, but these power factor values are given in percentage. Okay, so whereas if you go to the previous slide, see how the power factor values are given in 0.95 leading and lagging, whereas this one in this table, the values are given in 30% leading. Okay, but Peter will show you how to enter those values in percentage on a Fronius inverter. Okay, but that's just the difference sometimes you can find in the table. The Volt-VAR response mode table is very similar. As you can see here, you've got 207 volts, no power reductions, 220, no inverter can produce the maximum power, but as soon as the voltage increases above 250 volts, and if it hits the maximum 265 volts, then the inverter must reduce its power to 20% of the maximum watts capacity. Okay, so maximum watts capacity of the inverter. So these are just a couple of examples of the tables usually specified by the grid operators in the country. SA powers, they usually have this same tables, but they can also change those values in the tables depending on the voltage rise in the area, or how bad the voltage rise is in the area. Okay. So my colleague Peter will take over from here, and he will show you how to use the Fronius Excel tool to calculate all those set points for the voltages and power factors. Okay, so I'll hand over to Peter.
Okay, thank you, Sam. Hello again, everyone. This is Peter from Fronius tech support team. I'm really happy to be here to show you guys the practical part, which is how to calculate the Volt-VAR values and also the Volt-Watt values using those two Excel sheets, and how to put the values into the inverters. Sorry about that. So let's have a look at the first table, the first Excel sheet tool, which is the Volt-VAR mode, and then I will cover the second one, which is the Volt-Watt later. So as Sam was explaining in the previous slides, as you can see, there are 8 set points values that we will eventually calculate out of this tool and put into the inverters. So the reason why we developed this tool, these two tools, is we can only put in the percentage value into the Fronius inverters instead of the 4 different voltage references and also the power factor. We can't really put those values directly into the Fronius inverter. That's why we use these two Excel sheets to calculate the values. Also, as Sam was explaining in the previous slides, if your local distributor provides you the power factor in terms of the 0.95 leading, for example, and negative 0.9 lagging, then we need to use this tool to calculate the corresponding Volt-VAR values. But if your local distributor provides you the Volt-VAR percentage directly, like in the for the SA power network, they just give you the 30%, for example, and then the negative 43%, for example. You don't need to do any calculations. You just need to put those values directly into the inverters. So let's have a look. I'm just gonna make a few examples. For the first set point, which is CHQU 0-0, the 90%, how it's calculated is using the V1, the first reference voltage, 207 volts in this case, divided by 230 volts, which is the nominal grid voltage, then you get 90%. So if, for example, I change this to 210, as you guys can see, this value will change. All right, so the first step, you just need to put in the different voltage values provided by your local distributor into the correct position into the table. And then this for values will be calculated automatically. And for example, for this one, the Volt-VAR values, CHQU 0-1, it's determined dependent on this power factor. If I change, for example, to 0.9, it will change the value automatically. But like I said, if your local distributor give you this percentage value directly, you don't need to do any change. You just put in the values into the inverter. And for example, if I change this one to negative 0.8, this value will change too. But again, you just need to go by whatever value provided by a local distributor, put the values into the correct locations, and those Volt-VAR values will be calculated automatically. And then you just need to write it down, because we need to put these values later into the Fronius inverter, which I'm going to show you later. So let's have a look at the Volt-Watt, the calculating tool. Very similar to the Volt-VAR one. You also have 4 voltage references points. Again, these voltages will be provided by your local distributor, and this is just an example value here. Same thing here. You just need to put in the voltage into this 4 sections, and also the power output. For example, when the voltage at the inverter terminal is 207 volts, the inverter will produce 100%, so you put 100% there. And when the voltage is 220 volts, the inverter will still produce full power, 100%. When the inverter voltage is 255, it's still 100%. But when the voltage increases to 265 volts, the inverter output will reduce to 20%. So when you put those 2 values, it will calculate the derating gradient. What it means is, from 255 volts, when the voltage increases by 1 volt, the output power will reduce by 8%. That's what it means. So for example, guys, if I change to, if I change these values by 250, just an example, you will see this gradient will change to 5.3%. So that's how we use this tool to calculate. And you guys can request this tool. Just call us Fronius Tech Support. We can send you this Excel sheet, and then you can use this to calculate these 8 set points for the Volt-VAR settings. And you can use this table to calculate the Volt-Watt response mode, which is the derating gradient. Okay, so that's how we calculate these values here. So now I'm going to show you how to put those values into the Fronius inverter. The configuration of the Volt-VAR mode. So let's see how to put the Volt-VAR values into the inverter first. So let's say we are standing in front of the inverter right now. Okay, so this is the inverter front screen. First thing you do is press the third button from the left, 5 times. And when you do that, the screen will change. It will ask you for the access code to get into a profile menu in order to change the Volt-VAR values. If this window doesn't come up, normally means you didn't press the button hard enough, or you didn't press it like 5 times constantly. So just try again 5 or 6 times until this window, this screen shows up asking for the access code. So you can ask for the access code, which is also called the profile menu code. Just contact us on site, call Fronius Tech Support. We can give you the code. So the way you put in the code is by pressing the plus and the minus button, which is the first and the second button here, to change digits here. Once you got the correct number, you press the enter button, which is the 4th one, which is this one. to move to the next digit. You go one by one until you put in the correct access code. Once you've done that, you need to press the enter button again, and then the screen will flash, just like a reminder, make sure you put in the right code, and just press the enter button again. And then you are in the Profi menu. As you can see here, it says Profi menu code, Profi menu. The option you want to go is called reactive power mode, the one we want to enter today. So you just press the down arrow button, the second one, keep going down until you reach this option here, reactive power mode. And then you press the fourth button again. Let's select the first option, which is called react.p.mode. We enter that, press the fourth button, because we want to select the correct mode we are trying to implement today, which is the reactive power mode. So reactive power mode, it says here, and Q here stands for the reactive power. As Sam was explaining, U stands for voltage in this case. So we want to implement the voltage, the reactive power depending on the voltage. So this is the correct mode we want to add it today. So we just press enter, the fourth button. You automatically go back to the Profi menu. And remember the Excel tool I showed you guys earlier. The first option is CHQU0-0, which is when the voltage is, for example, 207 volts. 207 volts divided by 230, which is the nominal voltage power. So that give you 90% in this case. So you just put in the correct number there, press enter, and from here it's pretty straightforward. You just need to keep going to the next option, which is 0-1. Sorry about that. And then press the enter, which is the leading power factor, which is 30. In this case, is plus 31.22%, which means when the voltage at the inverter terminal is 207 volts, the power factor will be the reactive power value will be positive 31.22%. So those values are the one we calculated before in the Excel sheet. So we'll just keep going to the next one. CHQU1-0, same thing here, which is the second voltage reference point divided by 230 volts. Give you this figure, and this is only an example here. I mean, the actual value will be different according to the calculation. And then you just press enter. You will be automatically brought back to the Profi menu. Go to the next option, CHQU1-1. Enter that. Again, when the voltage is at this point, there's no change, as Sam was explaining in the previous slides. There's no need to change the power factor, so it's 0. The power factor is 1, no change. And then press enter. Go to the next option, 2-0. This is pretty straightforward as long as you got the correct calculation using the tool I showed you guys before. You just simply put in the correct value and just quickly go through each options. 2-1, no change, press enter, and then 3-0. So when the voltage is 110% higher than the nominal grid voltage, when that happened, the power factor will be lagging 43.58%, which is a lagging Volt-VAR value. And once you've done that, press enter. That's it. So that's all 8 set points put in to the inverter. So now let's have a look at the Volt-Watt mode, how to put in the Volt-Watt values into the inverter. So still within the Profi menu, the same menu, but this time instead of reactive power, we go to an option called Volt Dep Power Red. So this stands for voltage dependent power reduction, which is the Volt-Watt mode. So press the fourth button to enter into that menu. First, let's just check the enable limit. Press enter. So by default, it should be 250 volts. It says 254 here, doesn't really matter. So this enable limit can be changed upon request if you have a high voltage issue, but normally we just put it as 250 volts as a default. So the important parameter we want to change today is the derating gradient, which we calculated using the second tool, which I showed you guys before. Just enter into that. Yeah, so just real quickly, guys, for the enable limit, if you have like high voltage issue, the maximum you can put in, as stated in the previous slides, is the 255 volts. Just refer to the tables provided by your local distributor. Okay, so yeah, and again, this is the V3 voltage as stated in the table from the previous slides. So back to the derating gradient, we enter into that option. Again, this is only example 7.27, but whatever you calculated using the tool, you just put in the derating gradient percentage here. Again, using the plus and minus to play with the numbers. And then when you get the correct number, correct gradient, you just press the fourth enter button to confirm that. And now we've completed how to put in the Volt-Watt values and the Volt-VAR values into the inverter. But how do we know if the settings are successfully applied? How do we know that? So we can actually check it by, again, going back to the main menu of the inverter's front screen. You can see a setup menu here, one of the options. So go into the setup menu and go to info on the info menu. Go to device info, press the down arrow button, go to device info here. And then you can just, you will see this Q dash mode if you press the down arrow button, and you will see all the values are displayed. And again, this is not a real-time reading. This is just all the settings you put in previously. So if the value doesn't change, so that's normal because it's not a live reading. It's not a real-time reading. Okay, guys. So that's how we check it. If the values settings are successfully applied. So just a quick review for today. First of all, the first thing we do is calculate the Volt-VAR values and the Volt-Watt derating gradient using the Fronius Excel tool, which I just showed you before, which can be provided by us. I can send you this tool. And once you put in the correct voltage, reference points, power factor, and got the correct values, you just need to put the corresponding values into the inverter. The way I just showed you guys before, just putting the values into the inverter. And again, yeah, we can provide the Excel tool. So yeah, that would be the end of the webinar. Thank you guys. Any questions?
Yeah, thank you, Peter. So that was the end of the webinar. If you do have a questions, you can put your questions into the questions window of this software, and we will try to answer as many questions as possible. Thank you. Just the questions that these slides for the webinar we will be available on the platform, or we can send you a copy of the slides. The other thing I would like to mention here that we will upload this webinar on our YouTube channel. So if you would like to refer to some of the settings, you can definitely go to our YouTube channels and access this webinar later on. So we'll try to create the final copy of the webinar and upload it as soon as possible, probably in the next couple of weeks. Okay.
So
regarding the spreadsheet as well, the Excel tool, we can certainly email you that Excel tool, or once we get the email addresses of all the attendees, we can also email a copy of that Excel tool to you as well. Okay. Now, there was a questions about how about the additional settings in the QU settings, for example, the time, C at, etc. There are some additional settings in the QU setting as well, such as the time settings, but that's usually not specified by the local distributors. So we just leave that one as it is. But if it has been specified by the local distributors, then that value can also be changed. But generally, when we get a call regarding the Volt-VAR settings in tech support, mainly we just help installers with the 4 power factor values, and also the enable limit and the derating gradients values. And those are the values that are also specified by the local distributors. Another questions that's been asked, is it possible to have these values for the remote access to this setting to sort of save the times and energy? Unfortunately, at the moment, we cannot remotely change those settings. It has to be done on the inverter display screen using the access code. But I think, to my knowledge, our next inverter series, which would be released sometime next year, will have that capabilities where you can change it remotely. Okay, all those settings. Another questions that why do you not have these values as default factory settings? I guess it depending on the local distributors as well, because value they would like us to set on the inverters. So that should be coming from the local distributors. However, because our inverters are compliant with the AS NZS 4777, those default values in the inverters, when you select the AU as a country setup, are from that table stipulated in the AS 4777 standard. Okay, so those default values are from the AS 4777. But some utilities, like I said, some grid operators, they have this different voltage and also the power factor values, depending on the level of the voltage rise issues in the area. So if the voltage rise is really bad, then they may sort of specify different values in the table. Okay. Another questions regarding the U long time referred to. What does that U long time refer to in that Profi menu? U long time is basically referring to the 10 minutes average value. So the default value for that voltage is 255 on a Fronius inverters when you select AU as a country set. Really good questions. If you got a multiple inverters at the site and they are linked with the data cables in the master and slave fashions, then you will require to set this value on all the inverters individually. So you can't just enter those set points for the voltage value and the power factor only on the master inverters. You will require to set those values on all the inverters individually. Okay. There was another questions about the time constants in which the inverter will steadily adjust the power to the specific voltage level, and why we haven't covered that in the presentations. Like I said, those time constant value, which is, we'll leave that one as a default, but if it's required to be changed, I think it can also be done, but generally we don't really change that time constant value in the Profi menu. And I think that if the utility has specified that, then maybe let us know, and we can definitely provide you with the more informations regarding that. Okay. Is there a menu on the inverter screen we can go to check the Volt-Watt settings? So unfortunately, we cannot check the Volt-Watt settings. There's only an options to check the Volt-VAR settings, so we can see what are the 4 grid voltage values set and what are the 4 power factor values set. Okay.
Just another question from George. On top of the Volt-VAR and Volt-Watt settings, do we need to adjust any other values like the U-long time? We can change the U-long time settings if the inverter is giving the specific error code, which is 102 when the voltage is high.
Now, there was another question about we should just see the state 5, 6, 7 unless the inverter is trying to produce the nameplate output. You can not see that one as a 5, 6, 7 error. You will see the reductions in the power on SolarWeb. We are also working on adding the power factor channel on SolarWeb, so we can also see how the power factor is changing based on the grid voltage value. So we may add a channel, the power factor channel, under the analysis sections of our online portal, where hopefully you should be able to check the change in the power factor based on the grid voltage values. Okay. Thank you, George. Thanks, Ben. Like I said, this webinar will be available on our YouTube channels for your future reference as well. And we will try to get this Excel tool to you via email. So we are going to hang around for another 5 to 10 minutes. So if you have any questions, please feel free to post that in the question sections of this webinar software or tool. There was a questions about the CPD points for this webinar. We will send a list of all the attendees to the Clean Energy Council, and also once it has been done, we can notify you via email. So we'll or you can contact the Clean Energy Council with your name and or a company name. I'm sure they will give you the points, the CPD points. Okay, but we will let you know on the process how that can be done. So we are going to hang around here for another 5 minutes. So if you have any questions, you can put your questions in the question sections of the software. There is a questions from George. In the Volt-Watt settings, where does the enable limit voltage come from? That enable limit voltage is the V3 values, specified in the table. So you will see that in the Volt-Watt response mode table, there is a V3 value, and that's the enable limit that we need to enter on the display screen of the inverter, or under the When you go to the volt det power red, go down to enable limit, and that's the V3 value specified in the table. Thanks again, everyone, for attending this webinar. We really hope that you have got a really good understanding on what the applications of the Volt-VAR response mode and Volt-Watt response mode, and hoping that it will help with the voltage rise issues at the different sites. But if you have any questions, you can always contact our technical support hotline, and they will be able to assist you with your query. Okay. Once again, thank you.
Thank you.
And you enjoy have a great afternoon. Thank you.
Thank you, guys.